Alright gang, here we go. So this is Chem 2, Unit 2, end of Chapter 2. So we're going to talk about chemical nomenclature. Alright, we're going to talk about naming ionic compounds, naming acids, naming binary molecular compounds, and naming simple organic compounds. So this will be a bit of a doozy of a video here. Alright, lots of different things to cover, lots of different rules. Might have to watch it more than once and do lots of practice on your own. Alright. Inorganic nomenclature. First rule, always write the name of the cation first. Okay, cation goes first. If the cation has more than one possible charge, you write the charge as a Roman numeral in parentheses. All right. The only ones that have a possible charge, more than one possible charge, are the transition metals. All right. We're blowing through this fast because I figure you remember most of it, or should remember it fairly quickly from Chem 1. All right. So you write the name of the cation first. If the cation has more than one possible charge, meaning if it is a transition metal, all right, you're going to use the Roman numeral in parentheses after its name. If it happens to be a polyatomic ion, or a polyatomic cation, it will end in -ium. So really there's two big ones, right? There's NH4 plus and H3O plus. These are the two big ones. All right, this guy's ammonium. Oops. Thinks I'm ammonium, and this guy is hydronium. All right. If the anion is an element, then you change the name of the element so it ends in "ide." So instead of oxygen, it becomes oxide, nitrogen, nitride, etc., etc. If it is a polyatomic, you just leave it the heck alone. All right. So that's inorganic nomenclature in a nutshell. All right. Now we're going to move on to patterns. If you have oxyanions. So the oxyanions are guys where you've got a nonmetal connected to an oxygen, and you can have various numbers of oxygens that are connected to it. All right, these are most common in the polyatomic ions that you have to memorize. All right, so when you have two possible oxyanions involving the same element, the one with fewer oxygens ends in "ite." All right, so there's two possible oxyanions for nitrogen. You have NO2 and NO3. Okay, the one with less, 2, is "ite," and then the other one is 8. All right, sulfite, SO3, and then sulfate, SO4. Also notice that they have the same charge. Okay, and this is really handy for memorization. Okay, so notice how both the nitrogen oxyanions have a -1 charge, or 1 minus charge, and both of the sulfur oxyanions have a 2 minus charge. Right, this makes life a lot easier for memorization. Okay, NO2 minus, NO3 minus. All right, so really all you have to do when you're memorizing these is just memorize one of them. Okay, if you just memorize nitrate is NO3 minus, then you automatically know that nitrite is one less oxygen and it has the same charge, so it would be NO2 minus. Same thing with sulfate. Memorize sulfate, SO4 2 minus is sulfate, then one less oxygen is sulfite, and they have the same charge, SO2 minus. All right. Some other patterns to recognize. All right, in period 2, so this is in the second row, right? And we have groups and periods. The first period has only hydrogen and helium in it, so this is not, doesn't really apply. So in period 2, these are the oxyanions. Okay, so we've got carbonate. So you should know now that carbonate would be CO2 2 minus, okay, and then we have nitrate, which we just talked about. The maximum number of oxygens that anything in the second period has is 3. There's no CO4, okay. Notice that we don't have anything here. Okay, this guy here would be our oxygen atom, and it just doesn't make sense that oxygen would form an oxyanion, because then you just have oxygens attached to itself. All right, and then in group 7 we have fluorine, and fluorine is way too electronegative. It's never going to share its electrons with oxygen. All right, so that never happens. And then we have in the third row, the maximum for the third row is 4. All right, so phosphate, it has 4. Okay, sulfate has 4, and then perchlorate has 4. We'll talk about why perchlorate, why we throw that per in front of it in the next slide here. Okay, notice, so you should automatically know, at least these 4 right here, that, you know, the carbonate, nitrite, phosphite, and sulfite would all be one less oxygen with the same charge. Okay, And also notice, this is another pattern to help you, that the charges decrease as you go from right to left, or they increase as you go from left to right. All right? Or sorry, I said that backwards. They decrease as you go left to right, and increase as you go right to left. So nitrogen versus carbonate has 1 minus and then 2 minus. Okay, chlorine is 1 minus, sulfur is 2 minus, and then phosphorus is 3 minus. Just like their oxyanions. Pretty handy. All right. Now chlorine is special, okay, because chlorine has 4 versions of its oxyanion. All right. So the one that has most we say is perchlorate. All right. So that's the one with 4. Remember, it's on the third period. Okay. So it has 4 possible oxygens attached. All right. So oops, went wrong way. So this would be perchlorate, ClO4 minus. If we take away one of these oxygens, it becomes chlorate, ClO3 minus, all right? And then 1 less, so ClO2 minus would be chlorite, right? Notice that we follow the same pattern. Ite is 1 less than 8. And then 1 less than that, ClO minus right here is hypoite or hypochlorite, all right? So it follows this pattern going like this. Perchlorate, chlorate, chlorite, hypochlorite, all right? The simple one, so if you just have chloride by itself, so this would just be chloride, right? All right, and this just kind of walks you through. You can pause that and read that on your own. All right, so that's inorganic nomenclature. All right, so cation first, give the name of it, anion, all right, and then if it's a transition metal, you add the Roman numerals, transition metals. All right, then you've got polyatomics, and we talked about some patterns of oxyanions. All right. Now we're moving on to acid nomenclature. These are super easy. You just have to memorize 3 rules. All right. If your anion, okay, you're always going to look at the anion because the cation in an acid is always hydrogen. Okay, that's always your cation in an acid. All right. If your anion that's attached to your hydrogen is an element by itself, it would end in "ide" normally, right? Okay. But if it has a hydrogen, we know it's an acid, so then we name it hydrochloric acid or hydroic acid. So we put the base name of the anion in here. Okay, so this guy here, if we would normally call HCl, like based on the rules we just talked about, HCl would be hydrogen chloride, right? Hydrogen chloride. But we don't really that doesn't work because HCl is an acid, so we use the acid nomenclature. So instead of "ide," we change the "ide" to "ic" and add hydro in the front, and so it's hydrochloric acid is the proper name for HCl. All right. If our anion ended with 8, pretty much this only occurs if it's a polyatomic, then we change the 8 to "ic." Okay, you ate something icky. All right. So you ate something icky. So it becomes chloric acid in this case. Okay, so chlorate, ClO3 minus, we put an H on it, it becomes chloric acid. All right, perchlorate, right here, ClO4 minus, add the H so it becomes an acid, becomes perchloric acid. Notice that we left that front part. On this one, we never touched the front. Okay, this guy up here, we added the hydro because it was an element by itself. Down here, we left it alone and we just changed the H to X. All right. And then we also have, and then if it's an ite, it turns to us because you ate something ussy. No, that doesn't really work, right? You ate something icky, and then ites turn to us's. All right. So anyway, so your chlorite turns into chlorous acid. All right. Hypochlorite turns into hypochlorous acid. All right. And then here's some more examples here. So hydrochloric acid, notice, so this would usually be called hydrogen bromide. So we change the ide to ic, and then we change the beginning part to hydro. So it just becomes hydrobromic acid. All right. Now we have molecular compounds. So before we were talking about ionic compounds, meaning we've got a cation and an anion put together. So primarily that's stuff on the left-hand side of the periodic table combining with stuff on the right-hand side of the periodic table. Now we're going to be talking about molecular compounds. In molecular compounds, these are formed between 2 nonmetals. So these are 2 nonmetals bonding together, all right, 2 or more. Okay, so they're going to have a different set of rules to distinguish them because they're going to behave differently because they're molecular. When we name molecular compounds, we have to add these prefixes to them. Okay, so you got to memorize these prefixes. Most of them are pretty easy. They're just based on Latin. Mono is 1, di is 2, tri is 3, 4 is tetra. The ones that throw people off, tetra is 4, and hepta is 7. All right, almost everything else is kind of obvious. Tricycle, your dicycle, you know, your classic dicycle. You know, that was a joke. All right, and then you've got, okay, so when you name, so the one that's farthest to the left on the periodic table is the one you're going to name first. Okay, the one farthest to the left you're going to name first. All right, you don't change the ending to that name. All right, and then you add the prefix to whatever it is, unless there's only one of it. If there's only one of it, you don't add mono. So if it's on the left side of the periodic table, it goes first. You write the name as usual, add the prefix, unless there's only one, and then you just ignore the prefix. The second name, all right, the second element, the one that's farther to the right on the periodic table, you're going to change its last ending part to "ide," just like in the ionic compounds, and you're always going to add the prefix, right? Let's see, and this kind of just walks you through it. So the ending of the second element is changed to "ide." So this guy here, notice the carbon is farther to the left than oxygen, so we leave it alone. Carbon, notice that it's the first one and it's got a 1 here, okay, so that we don't say monocarbon, we just call it carbon. And then there's 2 oxygens, so 2 oxygens, so we call it di, and then oxide, not dioxygen, dioxide. Okay, this guy would be carbon tetrachloride because there's 4 chlorines, 1 carbon, so we don't put mono, and it becomes ide because chlorine is farther to the right. So carbon tetrachloride. All right, let's do a couple of practice problems here. All right, so this guy here would be K2SO4 would be potassium. Oops, potassium. All right, potassium, and then this guy's name is sulfate. So we have to ask ourselves, is potassium a transition metal? It is not a transition metal, so we can just leave it as is. We don't have to put in Roman numerals. So it's just potassium sulfate is its name. All right, the next guy would be barium. So we have to ask ourselves, is barium a transition metal? It is not, so we don't need Roman numerals. All right, so it would become barium hydroxide. All right. All right, then on this guy here, we say, all right, Fe is iron. Okay, so we say iron, and then, but iron is a transition metal, so we're going to leave spot for our Roman numerals here, and we're going to, so this is chloride. Now we have to think to ourselves, all right, what's the charge on this iron? Well, we know from last couple videos that chlorine here, each chlorine has a charge of -1, but there's 3 of them, so overall, these guys here have a charge of 3-, okay? 3-. So that means our iron had to have a charge of 3+. All right, so we'll put iron 3 chloride there for the name of that. All right, I've kind of written over some of the walkthrough of this. Sorry about that. All right, we'll skip that one. Let's see. And we named a bunch of them here. Yeah, we'll move on. All right, naming some acids. All right, so we're going to name these acids here. All right, so we're going to look at this guy. Well, we know that this polyatomic here is cyanide. All right, okay, so it turns into an ic, right? So this becomes cyanic acid, okay, or hydrocyanic acid. It kind of go either way. People kind of refer to it either way. All right, so because it's kind of like the exception because it ends in ide, and I told you before that ide changes to an hydroic, but because this is a polyatomic, there's a little bit of debate on this one. All right, now this guy here, this is nitrate. Okay, so this guy ends in ate. All right, so remember you ate something icky, so this becomes nitric acid. Okay, now just a side note, if you had H3N, that would be, you know, so you could call this an acid, although it's ridiculously weak, okay, and we wanted to name it, this would end in ide, okay, so this guy's name would be hydronitric acid, all right. Now notice how without this hydro in front, both of these guys would be just called nitric acid. So this hydro part turns out to be very, very important because it lets you know whether it's melt your face off acid, like nitric acid, or if it's like, you know, you could put on a baby's butt acid and everything would be just dandy. All right. This guy here would be sulfuric acid, all right? And then this guy here, ooh, so this was sulfate, right? This would be an 8. This guy here, SO3, is 1 less than our SO4, so this would be an ite. So that means this guy would be sulfurous acid. Pretty tricky, huh? All right, sulfurous acid. We're going to skip that one. Let's see if we can figure out what these guys are. So we got hydrobromic acid. So because we've got hydro, we know this is elemental. So it's just the element. Okay, so it's just going to be hydrogen with some element. Well, what element is it? Well, it says brome, so that's got to be bromine. So it's just hydrobromic acid, HBr. All right, carbonic acid. No, there's no hydro, so we know it came from something that ended with 8. Right, because of that ick. So it had to have come from an 8. So we look and we find out which carbon oxyanion ends with 8. Let's see. Shoot dang, 3. Yeah, took me a second. CO3, and it has a charge of 2-, so it's H2CO3. All right, so that'd be carbonic acid. All right, let's do a couple of binary things here. All right, so now this is where we're going to have so these are the molecular compounds because they're 2 nonmetals bonded together. So we're going to be applying those the prefix rules. All right. So this first one here, so that's sulfur. It's farther to the left, so it's sulfur. And then there's only one of them, so we don't add a prefix. Now the next one is oxygen. Remember, so it becomes oxide, and there's 2 of them. So we're going to put the I in front of it, so it'd be dioxide. Okay, sulfur dioxide. This next one here would be phosphorus. And then there's only one of them, all right, so we don't put mono. And then this guy, well, 5 was penta, all right, and then Cl5 would be chloride, pentachloride, all right. Okay, next one, Cl2O3. Cl's farther to the left, so we say it's dichlorine, all right, and then trioxide. Cool. All right, let's see. I'll skip those. All right, so that's all the ionic nomenclature. So there's that. So now we're gonna jump into organic compounds. So you got to kind of file this stuff away and realize when you have to apply different nomenclature rules. So when we're talking about ions, that's when we have a metal with a nonmetal or a cation with an anion. All right, so you're going to think about, all right, so I've got, is it a transition metal? Do I have more than one, charge possible? Do I need to add Roman numerals? Okay, does it start with a hydrogen? If it does, then I need to apply acid naming rules. And then if it's a molecular compound, meaning 2 nonmetals put together, do I need to apply the prefixes for the nonmetals? All right, so those are the ones we've talked about so far. Now we have to change gears entirely to talk about organic nomenclature. So organic chemistry is the study of carbon, right? Carbon is a plentiful element that has a lot of applications on Earth. So there's a whole section of chemistry that's studying carbon, organic chemistry. All right, and because it's so special, it's got its own system of nomenclature, mostly because these organic compounds can get ridiculously complicated. Because carbon, carbon can make 4 bonds, so it can bond with itself, with itself, with itself, with itself, with itself, with itself, et cetera, et cetera, et cetera, et cetera, et cetera, forever. All right. So, organic nomenclature is going to have its own set of rules. We're going to talk about how to name 2 different types of organic molecules. We're going to talk about how to name alkanes, and we're going to talk about how to name alcohols. All right, alkanes and alcohols. All right, alkanes are a single bond, or anytime you have a carbon chain or lots of carbons bonded together that only are made up of single bonds. All right, so these guys are all single bonds, so they're all anes. They end in ane. All right. All right, so that octane, you say, oh, I've got high octane fuel. That's a single bonded carbon atom or carbon chain, all single bonds. Okay, so when you're naming these, we're also going to use prefixes a lot. All right, but these prefixes are different than the prefixes you use when you're naming molecular compounds, so it can be kind of confusing. All right, so hang on to your hats. So here's your list of organic nomenclature. Okay. Prefixes. If you have 1 carbon, it's meth is the prefix. 2 is eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. All right, so you got to memorize those. Some of them are very similar, right? 7 in both is hept, that's nice. 8, 9, and 10 are all the same, right? That's nice. But 1, 2, 3, and 4 are all different, okay? And that's really what throws people off, all right? So 1 is meth, 2 is eth, 3 is prop. So if we go jump back here real quick, we can see we have methane, ethane, and propane, all right? And so each one has their own little thing they're doing, okay? So let's talk about just general rules for naming these guys. So step 1, whenever you're naming an organic molecule, is you're going to find the longest carbon chain. All right, find the longest chain. All right, find the longest carbon chain. So you're going to look at your carbon, and you're going to count the carbon. You're going to go 1, 2, 3, 4, 5, and just follow it around until you find the longest one. Be careful, because it can be tricky, because even though the longest one is not necessarily the one that's written straight across. Okay, so you find the longest carbon chain, all right, and I would go ahead and just kind of like shade it in with your pencil, or just kind of make note of it, all right, in some way. All right, and then the second one is you need to identify substituents. All right, this is a fancy word for branches. Okay, so these are the things that are attached to your chain. So you've got your chain of your longest carbon, and then off of it you're going to have substituents. These are your branches that are coming off of it. Okay, then after you've identified your substituents, where they are, you have to figure out the way to get the numbers of those substituents so that they're lowest. Okay, so you're going to number your carbon chain so that the numbers for the substituents are as low as possible. Okay, so the lowest numbers possible for the substituents. All right, lowest number possible for the substituent. Okay. If the substituent appears more than once, okay, repeat substituent, you have to add an additional prefix, okay, and these are going to use your molecular, okay, additional prefix, and these use the molecular prefixes. All right, so this is like well, mono doesn't exist because then it wouldn't be a repeat, so it would be like di, tri, tetra. All right. Okay, so at least you didn't memorize them for nothing for organic chemistry. Okay, then what you're going to do is, after you have the numbers, right, you have the numbers for all the substituents, all right, and you've got their prefixes, all right, you're going to organize these substituents, alphabetically. I know you guys are thinking I'm making this up. You're organizing your substituents alphabetically. All right, and then once they're organized alphabetically, okay, you write out the name. Okay, write the name in alphabetical order. Okay, alphabetically. You write the name alphabetically. And with dashes between numbers and letters. You guys are going to think I'm nuts. As I'm saying this out loud, I realize how complicated it sounds when you're hearing it for the first time. Write the name alphabetically with dashes between numbers and letters, and commas between numbers. All right? All right. Here we go. Yeah. Okay? Now, if your alkane has an OH in it, that's an alcohol. All right, and so instead of calling it an ane, we get rid of the E and change E to OL. All right, so if it has an OH, okay, if it has an OH, the E goes away and it becomes OL, right? OH goes away, it becomes OL, OH, OL. See that? Notice also that this 1 here suddenly appeared, and that's because this alcohol could appear here on the end, or it could appear here in the middle. So that 1 tells us where it is. Because it's 1, it tells us that it's on one of the end carbons. Okay. Another acceptable way of writing this that you might see, propan, and then -1 hyphen all. That's also an acceptable way of writing that. All right. Okay, so you name it almost exactly the same, only now you've got an alcohol, so that becomes OL, and you have to put a number in front of the base at the end. All right. So just a side note here, if you happen to have two molecules that have the same chemical formula but different structures, these are called isomers. So there's one propanol, that's what we just talked about, is 3 carbon chains in a row, and then the alcohol at the end. And then we have 2 propanols, so we've got 3 carbon chains, and then the oxygen on the middle one. Okay, so that 2 tells us it's on the second carbon, 1, 2, 3, right? Whereas this guy would be 1, 2, 3. Remember, we're always going to number our carbon chains so the numbers appear on the lowest. So that oxygen's on this carbon because it's on number 1, all right? And then this carbon here gets on number 2, all right? Notice both of them have the same formula of C3H8O. All right, so here we go. We're going to give the empirical, molecular, and structural formulas for the straight chain alkanes, N equals 5 and N equals 7. So N is the number of carbons. All right, so empirical, molecular, and structural formulas for the straight chains. So N equals 5. So that means we've got 5 carbons. So we've got C1, 2, 3, 4, 5 carbons, and then we're going to fill them up with hydrogens. All right. Remember, each carbon wants to make 4 bonds. All right. Remember the octet rule. All right. Sneezing trees. Yeah, anybody sneezing trees? All right. So 1, 2, 2, 2, 2, 2, 2, 2. All right. So there's our structural formula: 1, 2, 3, 4, 5 carbons. All right. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. So our empirical formula, or our molecular formula, would be C5H12, right? And because 5 is a prime number, this is the same. So this would be empirical and molecular formula. For N equals 7, we do the same thing, right? We've got 1, 2, 3, 4. Dang it! All right, let me erase this. All right, so we got 1, 2, 3, 4, 5, 6, 7. Yeah? And then we're going to fill this sucker up with H's. All right, so H, H, H. Oops, I forgot that. H, H, H. There you go. So this guy would be C7H16. All right, we got 6 hydrogen. And once again, because 7 is a prime number, the empirical molecular formulas are exactly the same. Remember, if you could divide them both by a smaller number, then you would change that. All right. Draw and name all the possible isomers of hexane. So this is where life gets more complicated. All right, so we got to figure out all the isomers of hexane. So remember, hexane, hex means 6 carbons. All right, so let's start over here. So we got 6. So let's just draw them like this: 1, 2, 3, 4, 5, 6. All right, so now we're going to draw our H's. Okay. Oh my goodness, maybe I won't draw all the H's on the rest of them. I'm sure you get it, and this is just thrilling video watching. All right, so there's all my H's. Okay, so so the name of this guy would just be regular old hexane. Now you could be fancy and add an N in front of it just to show that it's normal hexane. Okay, and really the N doesn't stand for normal. It means that it's in a straight chain, but we could call it normal hexane if we, All right, so we could also change this guy up. We could take one of these carbons that are in the end and put it in the middle. All right, so if we did that, it would look something like this. So we'd have 5 in a row like this, 1, 2, 3, 4, 5, and then we'd have 1 coming off of it. I'm not going to draw the hydrogens just to save us time here. All right, but you could see, if you really wanted to, you could count them up and see that it's got the same number of hydrogens, even though it comes off as a branch here. All right. So if we do that, we've got 6 carbons, all right? So now it's got a new name. So the longest carbon chain here is 5, right? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Notice we can count it from either direction, or 1, 2, 3, 4, 5. So now we have to identify our branches. So if we do our carbon chain just straight across, that's 1, 2, 3, 4, 5. So we've got a methyl group, right? So this has a methyl group coming off of it, all right? So we'll write out methyl. There's no other groups coming off, all right? So that's just the methyl, all right? Now we have to figure out the numbers and put the numbers on the lowest carbons. So if we count from this way, methyl, it would be 1, 2, 3, 4, so it would be on a 4. If we count from this way, it'd be on a 2. So we have to count from left to right. So this would be 1, 2, 3, 4, 5. All right, so that means this would be 2-methyl. All right, usually we'd have to list them out and change them alphabetically just to make sure we had them all in the right places, but we don't have to do that here. Okay, because there's only one carbon, or there's only one substituent, so it's just, there's no alphabetizing necessary. So it becomes 2-methyl, and the name of the 5 chain is pent. There's no alcohol, so we write just pentane. So it would just be 2-methyl pentane. All right. All right. So we've got some other ones here. All right, life's going to get really exciting here in a second. The next one, we could take this guy here and just put him on the middle one. That one's easy. So 3, 4, 5, and we'll put this carbon right here. Notice that these are exactly the same. The only difference is we've moved this carbon over. So instead of 2-methyl pentane, it becomes 3-methyl pentane. All right, that one's easy. So it becomes 2-methyl pentane instead of 3-methyl pentane. All right. So what else could we do? Well, what if we took another one off the side and we stuck it and we made them share a carbon? Remember, carbons can make 4 bonds. They don't always have to bond to hydrogens. All right. So if we take, so what if we put 4 in a row, 1, 2, 3, 4, and off of this one we put 1 carbon here and we put 1 carbon here. Still hexane, right? 1, 2, 3, 4, 5, 6. Okay. Where there's 6 carbons and 14 hydrogens, just like normal. All right, so just like the N-hexane, so it's still an isomer because it's got the same structure. All right, so now we got to figure out how to name this sucker. So the longest carbon chain here is 4, right? 1, 2, 3, 4. All right, so 4. And so now we got to name our substituents. Well, off this guy, we've got a methyl and a methyl. So we've got 2 methyls. So it would be a dimethyl. Remember, if there's 2 methyl, we call it, if there's 2 of the same substituent, we're going to call it di. All right, now we got to figure out the numbers. All right, so that carbon, if we name it from right to left, we go 1, 2, 3, 4. So it would be a 3-dimethyl. If we name it from left to right, 1, 2, 3, 4, it would be 2-dimethyl. So that one's easy. Now, one trick that I didn't really point out is because there's 2 of them, we have to put 2 numbers. And remember how I said if there's numbers next to each other, you put a comma. So it would be 2, 2 hyphen dimethyl, and then the longest carbon chain is 4, and that was bute, so it would be dimethyl butane. Okay, 2,2-dimethyl butane. All right. And then finally, the last one is we could take these guys and put them on opposite carbons. So what if we did 4 in a row here, 3, 4, and then we do this guy and we do this guy. All right. So we still got 6 carbons, we got 14 hydrogens, but now our carbons are on different things. So it's still dimethyl, okay? But one of them is on a 2, right? So if we count it, it would be a 1, 2, 3, 4. So we'd want to have a 2 and want to have a 3. And if we go the opposite direction, 1, 2, 3, 4, 1 would be on a 2, 1 would be on a 3. So it doesn't matter which direction we count, we have a 2 and a 3. So it would be a 2, 3 hyphen dimethyl butane. All right, so those are the 5 isomers of hexane. Okay, so you can see how even though we just have 6 carbons, life gets really complicated. C6H14 on all of them, but there's 5 very distinct carbon structures, and the name is really what allows us to know that they're all different things. All right, we're going to just practice naming a couple of things here. I was just checking to see how close I am to the end. All right, so we got to name our carbon chains here, or we got to find the longest one. All right. So this nomenclature is called condensed nomenclature, is the way this is set up. The carbons are connected to each other, and the hydrogens are coming off of the carbon that it comes after. All right, so the way this is set up, and I'll just draw it once here. So this carbon is this carbon here, and that's connected to that carbon, which is connected to that carbon, which is connected to that carbon. And then that CH3 means those H's are coming off of it like this. This isn't pure condensed nomenclature. It's kind of like a hybrid of structural and condensed. All right, so this means here, see that H? That means there's one H coming off of it, and then a C coming off of that, and then that C has the three H's coming off of it like that, and then etc. Like kind of like that. All right. So you got CH3, CH2, CH. So anyway, we don't have to read the whole thing. So we're just going to find the longest carbon chain. So let's start counting. So we got 1, 2, 3, 4, 5, 6, 7. All right, so 7 if we go straight across. 1, 2, 3, 4, 5, 6 if we go down. So that's one short, so still straight across. What if we go 1, 2, 3, 4, 5? No, that's not good. 1, 2, 3, 4, 5, 6. So it looks like 7. All right, so we know that we're going to have some sort of hept. So I'm just going to make a note to myself that that's 7. All right, so now we got to identify our substituents. They're both CH3s. So that means we're going to have 2 methyls. So we'll just write dimethyl here. So we've got dimethyl. All right, and now we have to figure out what numbers to stick them off of. So if we start counting from this end, we get 1, 2, 3. So 1 on 3, 4, 5, 1 on 5, and then 6, 7. Okay, so it'd be a 3 and a 5. If we start from the right, it would be 1, 2, 3. So 1 there, and then 4, 5, 5, 6, 7. So it'd be the same, 3, 5, no matter what. And dimethyl, so they're the same. So we don't have to worry about alphabetizing or anything. So it'd be 3, 5 hyphen dimethyl heptane. All right, it's kind of fun. It's like solving a puzzle. All right, now this next one here. Now we're gonna name our. Oh, I should. Let's pretend this is a CH3. We're not talking. I meant to change that to a CH3. My bad. Okay, we're gonna pretend that's a CH3. So anyway, so let's count our carbon chain here. 1, 2, 3, 4, 5. So that's 5. 1, 2, 3, 4, 5. Still the same. Okay. So we got 5. So this is gonna be a 5. I'll just make a little note that it's 5. Oh, notice we got an alcohol here. All right. So this means we're gonna change. We have to remember that number for the alcohol. All right, and we got to remember that that the alcohol changes the E to the OL at the end. All right, so that's not like a substituent, kind of like the other carbon chains we're looking at. All right, so 5. So we got, so our only real substituent here is this guy. So that's a methyl group. All right, so methyl group. All right, and then we got to figure out our numbers now. There's only one of them, so that's easy. We don't have to alphabetize because there's only one substituent. All right. So we're going to count. So we go a 1, 2. So it's on a 2, 3, 4, 5. Okay. So it'd be a 2 and a 4. All right. 1, 2, 3, 4, 5. A 2 and a 4. Now here's the tricky part. Alcohol, because it's more powerful of a substituent or something like that, that number gets preference if they're tied. All right, so this is a special case because they're tied. We're going to give the 2 to the alcohol. All right, so this would be 1, 2, 3, 4, 5 is the correct way to number it. So it would be 4 hyphen methyl. All right, and then 2 hyphen, and then 5 is pentanol. All right, 4 methyl, 2 pentanol. All right, here we go. So back here. And the next guy here, now we got to find our longest carbon chain. Now this one might be a little tricky. So we got 1, 2, 3, 4, 5, 6, 7. If we go straight across, 1, 2, 3, 4, 5, 6, 7, 8. Ooh. So if we go over and then cut down, then that's 8. So that's the longest carbon chain. We got that 8 there. All right, so we got to be careful. So what kind of constituents do we got? We got a methyl group right here. All right, so I'll make a little note. Because I've got more than one, I'm just going to list them. So we got a methyl group there. And then here we got a 2 carbon chain. So that becomes an ethyl group. All right, so a methyl group and an ethyl group. So now we have to worry about alphabetizing. E comes before M, so this one's going to get labeled first. All right, now we got to figure out our numbers. So remember, because they're both carbon substituents, the the numbers don't matter. We're just going to try to get the lowest numbers total. All right, so here we go. So if we count from here, then we get a 1, 2, 3, 4. So the ethyl would be on 4, 5, 6, and the methyl would be on a 6. So it would be a 4, 6. If we start from the right or from the left and go right, it would be 1, 2, 3. So the methyl would be on a 3, 4, 5, and so it would be a 3, 5. So obviously 3, 5 wins. So that means the methyl would be on a 3 and the ethyl would be on a 5. So the name of this guy, we got to do ethyl first because it's alphabetically. E comes before M, so it would be a 5 hyphen ethyl. Remember, a hyphen comes between the number and the letters. So 5 ethyl hyphen 3 hyphen methyl. And then the name of the thing, and it's an 8. See, a good thing I wrote that down. Octane. Okay, so that would be the real name of it. 5 ethyl 3 methyl octane. All right, so now let's do a couple where we go backwards. These I think are a little easier. So I like to start with the back end. So this is nonane. All right, so that means we've got 9 carbons in a row. All right, so you could even just go ahead and write it out. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. All right, so we got 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and then we've got a couple of chains. We've got on 3 and 4 we have methyls. So we'll just go 1, 2, 3. So 3 we've got a methyl, and 4 we've got a methyl. All right, that's easy. And then on the 4 we also have an ethyl. So up here we've got another ethyl, and I'll just go off to the side here. And so this would be the carbon chain. Then we could just go through and label in all our hydrogens. 1, 2, 3, 4, 5, 6. Tons of hydrogens. Lots and lots of hydrogens. So this carbon, be careful, would have to have 2 hydrogens. 1 there, 1 there. This one here at the end would have 3 hydrogens. All right, so we go 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3. All right, so that would be the structure of dimethyl 4 or 3,4-dimethyl 4-ethyl nonane. Don't you love organic chemistry? Aren't you so excited for those of you who are going on to college to study chemistry or pre-med or something that we're gonna have like a whole year of this craziness? And this isn't even as crazy as it gets. Let's do one more. All right. So this one, you won't have one like this on a quiz or anything because it's got these fancy halogens in it. We got bromo and chloro, but you know enough to solve it. All right. So the chain is a butane. So we got 1, 2, 3, 4. All right, 1, 2, 3, 4, because but is 4. All right, we know it's an ane, so it's all single bonds. We don't have to worry about an alcohol. All right, on number 2 carbon, we have a bromo. I'll bet you can guess what a bromo is. That's right, it's a bromine. So we'll put a bromine on 2. And then on number 1, we've got a chlorine. All right, that's what chloro means, so Cl. And then everywhere else, we're just going to have hydrogen. So H, 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 H. Cool? So that would be 2 bromo, 1 chlorobutane. All right, this was quite the lengthy video. I hope you enjoyed it. Practice lots and lots of text problems. We talked about ionic nomenclature with transition metals and polyatomic ions. We talked about acid nomenclature. We talked about molecular nomenclature, and then we wrapped it all up by talking about organic nomenclature. All right, do lots of practice. Let me know if you have any questions, and I'll see you on the flip side.